Oh, sound is good. Oh, we'll continue the lesson about cluster means. Um, then today we'll walk over an example. You are simplified the data, but it's kind of close to a real example. So here I have a group, a very simple data set with only two variables. Yeah. It only has two feature X and Y. And so we are going to cluster, divide them into clusters and to find what is the best way to divide these dots. Um, so but first, get a plot to visualize this data. Since it's only 2D, so we can easily visualize this. So by observation, we can see maybe a good way to divide these two data is to divide the dots in this line, right? Here, probably the first cluster, and then here it's a second cluster. So recap the lesson we learned on Tuesday. How does this algorithm work on the dots? How does the algorithm um, cluster these dots? Recap what we learned on Tuesday and what is the first step it does and the second step it does. Because I want to recap this because a lot of you missed the lesson on Tuesday. So let's try this, okay? The first thing this algorithm do is to first thing it does is to what does it do first thing?
Does it pick a centroid?
A centroid, yeah, randomly pick up one centroid. That's the first thing. Oh, the cluster. Centroid is like the center of those clusters. Okay, the cluster you are going to find. So, for example, let's randomly pick up maybe this one. Okay, this one as the centroid, centroid one, and then the second step it does is let's try like three cluster. Okay, let's try three cluster. Then the second thing the algorithm does is to pick up another random point, randomly pick up another point at the second centroid. So, but we said it actually doesn't randomly pick up. It pick up the furthest point at the second centroid. So maybe this one as the second centroid. And then if we want, because we want three clusters, so we'll pick up a third centroid. Third centroid could be the middle, that has the nearest the nearest distance to both dots. So if you add this one together, this one is probably the nearest to both, right? The sum of the distance might be the smallest. So we will pick up this one as the third centroid. And then what's the next step in that? Already assumed these three centroid now. What the next step it does? To classify these dots. So the three, all these, of course, all these are closer to the first centroid. So these will be centroid 1. If we say yellow color, then yellow, okay? And all these will be yellow dots, right? And here, these of course it's closer to this one. This will be this is the red, okay? These will be all be red. This one is actually not sure, right? This one will be this one, probably centroid 3. So we'll do these as the third centroid. This one also, okay? Third centroid, and these are likely to be the second centroid. Right? But it's not the final result. What's the next step it does? After finding the cluster, what's the next step?
Isn't it something like the variance between all those points to that?
Yeah. Yes. So we'll find we'll move the centroid. This is the temporary cluster we find. Obviously, for this new cluster, this is not the centroid. After getting this cluster, it will find a new centroid that has the smallest variance to all these dots. So that will be the new centroid. For example, this new centroid for all these dots, it's probably around here. This will be our new centroid. Okay, centroid, still yellow. And then here for this one, the new centroid will be probably around here as the new centroid. So still C2 and red. And for all these 4 dots, find a new centroid probably around here. It will be around here. Or maybe a little bit closer to here as the new centroid. Blue, okay? And then what it does is using these new centroid, it will classify all these dots again until the centroid doesn't, all these centroid do not move anymore. So for this one, these are still belong to this cluster. It doesn't need to move, right? It don't need to move. So this one is kind of a fixed. And for these, so for this one, these are of course still this centroid. They are closer to this new centroid. They don't need to move. But for this one, it may be merged to this cluster instead of this old cluster. And then this new cluster will be only three dots. And then what it does. So this shape changed a little bit. What it does is it has a new cluster and then find the centroid find the new centroid again with this new dots. And here, let's find a new centroid again, probably moved to here. Until all these centroids do not move anymore. That's the result we got. Okay, so in some pick up a random centroid, and then a cluster, classify these dots, and then find a new centroid after forming these cluster until the centroid doesn't move anymore. Okay, that's a process behind this algorithm. So like this one, maybe like after two rounds, two repeats, the centroid will be fixed and then find the best result. Okay. Oh, next one, let's see. Yeah.
So
Yeah,
just
John.
to clarify, you said you changed the original centroids
Yes.
and come to make a new centroid to
Yes.
show little variance.
Yes. Oh, all the centroid should be the dots, the position with the smallest variance. The average smallest was of all the dots should be the smallest.
So is the outsides like our first centroid, the one?
This one, it was the original.
Yeah, I'm saying like are those included?
These are all included in this cluster, this yellow cluster.
Okay.
Yeah, and this is the first centroid we randomly picked up, but obviously for this cluster, it's not the centroid, right? It's on the edge of this cluster.
You said it's underage?
It's on the edge, like these dots, it's on the edge of this cluster. It's not the center. So after forming this cluster, I reposition the class, the center. Find the new center. It might be here. This one might be closest to all these dots. And then after finding this new center, reclassify all these dots. For example, in this cluster, it doesn't move anymore because all these dots belong to this cluster. But for this cluster, originally, the centroid we pick up was here, so this one belonged to this cluster. But after move the center to here, this may be added to this second cluster. Then what I need is to reposition, because you added a dot, the center will change. So I move until the center doesn't change anymore. A fix. That's the final result we got.
Okay.
Okay, next one, let's see, the area, what's the result it got if we use this code. For the code, it really like everything else we did before. So what you needed to do is to import the package. And then use this k-means. K-means, I'll just say it's model, okay? Model plus k-means. And then you want to tell it the number of cluster you want. For example, I want 3 clusters. And then you use this model to fit the data. Data is a df. Do we need to get a specific feature? I think we can use both feature. So it's just df. um, that's a model we fit. And then if we use the model to predict the existing data, DF, then it will give us the result, like how they are divided into different centers. There's some warnings. It tells me to add the same. Still a warning. I'm thinking to change the system environment, but I'll skip it here. So now it tells us like each case what center, which cluster it belongs to. So we ask it to classify 3 clusters and it gives us 3 classes. Let's see if the result is the same as what we did, okay? Next thing I want to do is to color these dots. So what we can do is to get the cluster labels, cluster centers, okay? This code will return the centers of these clusters. So this is the model we built, and this attribute it gets the centers of these. We return the position of these centroid. Let's put these on the on this plot. On these plots. Centroid. Oops. 3 dots. So this will be the X and this will be the Y, right? 0. See, the result we got pretty much as what we calculated. These are the first cluster and this is the second cluster. I don't know what the dots belong to. Likely. It's likely either one, right? Not sure. Only this one we are not sure, but everything else is the same as what we calculated. Yeah, and you can draw manually and try to like is the process we did. You can try to pick up another 2 centroid at the initial centroid, another 3 centroid at the initial centroid, and then converge and you should get the same result as we do here. Of course, we can like color them to see. We can add a color to these, okay, and see the result. This trunk is just to change those labels 1 to 0 to these colors, blue and red. So it's an empty list, and then I change this using this index to change this list to blue, red, and green. Okay. And then we give this color to these dots instead of using pure red. So this plot will be little bit better. I didn't take it this label. So it's not quite the same as what we did, right? Let's see, okay. Did wrong. So let's return a different result. So obviously wrong. Did I code it wrong? Must code it wrong. See, these are the centroid, so centroid. Okay, so this one is the same. This one is the same as we did. And the centroid are the same. Let's refresh this and see if it gives us a different result. Obviously, the last time around this, I made it into different centroid. See this one, it still give us the same result. No, only the
Centroids,
centroid one.
like if you run this enough times with the centroids move.
So let's observe these. I may give us a slightly different data every time we run it. Let's see if it changes. Okay. The result may change slightly. It will change differently. And let's see what we got this time. But still pretty the same result. The last time we got it was like a one cent cluster here, one cluster here, and then the whole cluster here. So that may give you a different result. So it depends on like how the first random points the system pick up, so the result will be slightly different. But it should be similar. It should give you the similar result of the center. However, you see, the centroid should not change if these are like the same cluster, right? This is the same cluster, and this is the same cluster we got as the last time. Then these centroid should be exactly the same as the last repeat. Let's run this again. Let's put them together so it will be easier to see. This changes. See, this is different from what we got. This time, these three dots are in one center. In one center. This is one center. Let's see if I delete this one. The result will be fixed or not. I delete this one. Every time I run this, let's run this a couple times. Doesn't change anymore. See, I think this auto init that may like make the points completely random, and that makes the result change. So here it's the auto, okay, run with different centroid seeds. So I believe that this argument in init auto, this one matters. It probably changes the points to be completely random. That's why we get a different result at the end, or else we should get a consistent result. So I will do a little bit more research and to see how does this argument matters. Because last year I used this algorithm, it doesn't even have this argument, so it's a little bit different. Okay, let's move on to the next key points. And now with this algorithm, of course, you can predict a new cluster, a new point, or if any new points coming in, for example, there's a point here, then it calculates its distance to these centroid and to decide which cluster belong to. So if it's a dot here, it's closer to the centroid, and it will be the prediction result will be red. So that's how it works for the later prediction. Any question here? Okay. Okay. We mentioned how to find the optimal K. So K could be 3. Here we use the K equals 3. But K could be 2 cluster. Obviously, this two cluster in more. If we by observation we see two clusters, right? This cluster, it's clearly divided these. So how can we decide which K is better? It's like the K-means you do a loop and to go over these Ks and find the best K. The best K, there are two metrics. The first metric, what we mentioned, calculate the variance within this cluster. So the average variance within this cluster, if the variance is smaller, that means that the dots are all closer to the centroid. So this cluster is better. But when the K goes up, and then those clusters are smaller. So the variance will be, the average variance will be smaller, right? However, we don't want to divide all these dots into very small clusters. So there's an optimal K. So this K will get the average distance. So the average distance is all these distance added together and divided by the number of dots. Right? And if the cluster is smaller, of course, if they're like we do like a 5, we divide it into 5 or 6 cluster, of course, the average variance will be smaller. The average variance changed from this distance to this distance now. If you use these clusters, right? Like these two, one cluster, then the variance to the centroid is this distance. Of course, the more cluster you have, the smaller variance you have. That makes sense? Yeah, the average of variance will be smaller. However, it should decrease. It should decrease, and at some point, it doesn't decrease that much. We decrease very sharply, and at some point, it doesn't decrease anymore, or slightly. It will still decrease slightly. So that's called the Abel point we want to find. The Abel point is the best case we want. Code. In code, what we do is to get a loop. Get a loop for this code. K means or K for sets larger than 2 to 11, I mean. And we use this 3 should be replaced by K. So K goes from 2 to 11. And then model fit. We use this new model to fit this data, and then you print out the variance, the average variance of this model, which is called inertia. I believe the code is called inertia. Okay, it's the inertia. That's the attribute for average variance. and we save it in a list. So this, see this inertia, this number, it goes down as the k goes from 2 to 11, right? It goes down all the time. Then if we plot this number, I plot this, x should be NumPy range. To 11, 2 to 12, actually should be 2 to 12, right? And then the y value is the L. If we import the wrong number, oh, it should be 2 to 11 because 11 is excluded here also. So I was wrong. Actually only go from 2 to 10. And this should be 11. You see, goes down from 2, 3 is still decreasing. So the upper point look like around here or around here. Yeah. Should be around here, look like, right? But see, in some cases, you're not quite sure what is the upper point here. So there's a function you could use called, it's called knee locator. So this is the result I got last time. Why the result today is a little bit different? Okay. I think I see. So this, I didn't include one. To go from 1 to 11, and he will give us the same result. So it was because I cut this part out. I didn't start with 1, so this upper point, this should be the upper point, but because I cut it out, that part, it's lost. It's actually the upper point. For the first time I started at 2, so this part of the picture is lost. That makes sense. So what I did was wrong. It actually should start from 2 or start from 1, cluster 1, and then see we still have this upper point here 2. Okay. So yeah, I did was this part is I cut it out this left part. That's why we lose that upper point here. But in this picture, it's obviously this is the upper point. So, but yeah, in some cases, you cannot. It's not easy to detect the upper point. So what you do is to use this knee locator. Okay, the knee locator, you give it the range, and then you give it the number, the average variance list, and then it will return you the best point. Of course, like this kind of it tells me to install every time. Okay, let's move on to the next one. I'll mention there's another metric for finding the best case, which is called single coefficient. It's similar to, it's based on the other method we just learned, but it added another another like a factor, another factor. What it does is means what it does is I think you should not just evaluate the variance within this group, but also evaluate its distance to other groups. If the distance to other groups are further, okay, these clusters are more obvious, right? That makes sense. So it doesn't only measure whether the points in this cluster is close, but also it measures if your clusters are far away from other cluster. So like this one, it's very far away from the other cluster. Of course, it's good. Yeah, so imagine if we divide them into smaller clusters, these clusters will be close to the other clusters. So that's not a good result. So what we want is that the cluster, those dots in the cluster is close, and between these clusters, they are far away from other. So that will be easier for us to classify it out. Okay, so that's called the C-Hill coefficient. For example, here we got this result, and if we need to calculate the C-Hill coefficient, how do we calculate it? I calculate the cluster 0. I calculate so the C-Hill coefficient of this one, coefficient of this one. Yes, so C-Hill coefficient of this one is the distance to these two dots and average divided by 2. So this is the A. Okay. This is the distance within the cluster. So the distance within this cluster is these two distances added together divided by 2. And this is the distance to its nearest cluster. So that's the cluster 2, obviously. So this is this distance plus this distance and divided by 2. That's the B. Okay. B is to 25. The dots 10, 10 to 25, and 10, 10 to 25, 4, and then divide by 2. So this is the B number. And then the C-Hill coefficient is 1 minus 2.914 divided by 15,983. Yeah. Sheet. Oh. So the generally measures cluster cohesion and the separation both together. So there are a lot of dots. Then what is the final result? So here we calculated one dot, the coefficient of one dot, right? And the whole result, how does it calculate? How should it calculate the result of this whole picture? It goes over, I would assume it goes over each point and calculate the single coefficient of each point and then do an average. Let's see, okay. We have you can research and to see how it does. So see, it's a metric measure how we all combine. I believe it should calculate each point. This, yeah, most of the article doesn't explain, but I believe they calculate the coefficient of each point and then do an average. You can research and see what it does. These are just some of the details about the algorithm. And using this stereo coefficient, usually it returns the same result as the usually it returns the same result as the Abel method. Okay, so it's the same. You goes over a loop, and then here you use this single coefficient score. And then for the single coefficient score, you just find the should it be the largest or should it be the smallest? Think about it. Should it be the largest or should it be the smallest? A is the cohesion of the cluster line. A should be, you want A be smaller. Want A be smaller. So this number should be larger. The larger the better. Huh? We want A to be the smallest and the B to the separation. That's the separation, the distance from other cluster. The separation, we want B to be larger. So this one should be the smallest, and this one minus this one should be the largest, right? So we want this pseudo coefficient to be the larger, the better. Am I correct? Am I correct? Yeah. So here, you just find the largest number. Okay, you doesn't need to plot it and find the like a sharp point. this should return the same result. You see, when k is 2, this number is the largest. So that's the best case design. Okay. All right. Next thing. This is just a plot of the result. It will continue to decrease. It's actually not continue to decrease. K equals 2 is the largest. It continue to decrease, yes. Doesn't continue to decrease. It could be like a zigzag, and the highest point is the best. Could goes down, or could goes up, and the highest point is the best. Okay. The last one is that eventually, when we want to rebuild the cluster, eventually the purpose is it will be easy for us to predict the future data points. We understand, help us understand how these people can be, how these data points can be best classified. Right? We want to find the rule of whether feature A is the best factor, or whether we cluster them by their gender, or whether we cluster them by their habit, right? Or sport exercise habit. So the last thing what you can do is to get the box plots of these results. What you do is what you do is to use the box plots. And you visualize this box, visualize these data. So this is the DA and the Y. The new DA, we add the result of the classes. We added the result of the labels as a new column called classes. K equals 2, right? K equals 2, and then we use this model to predict all the points. Or we give this result as a new column, as a third column for the data frame. So now this new data frame, this one first. This is a new data frame, and each data point has a class now, and into different clusters, to different class. And so we want to understand how, like, are these clustered, divided by this male or female, this gender, or these classes are divided better by their heights. It could be divided by their gender, or it could be divided by they could be like cluster better with their with their weight, maybe, right? That's why it could be weight or height. So what we want to see is which feature is a better factor for clustering these. So this classes and want to build this box plot. What do you think? Does this feature a good feature to divide this data? Why?
Very far apart.
Very far apart. Is it good or bad as a factor to divide the data point?
Good.
That's good. Yeah, right. So this is a very clear line, maybe 5 or maybe 4. All these people under 4, under like this height, okay, they are clustered as 1. They are classified as 1. And all the people above with their height above 4, okay, they are clustered as 1. So that's actually it's the same as what we did with the classification. Yeah, the box plots, they are far apart. Okay, that's a good feature. That's a good feature for deciding the influencing the classes. Right. So let's see if we use this Y, the second feature. Okay, second feature we named it Y. How about this one? Actually also pretty good. Divide at here, at this line. However, there's one outlier here. If you use this line 6, there's one outlier. This one, it should be in this blue box, but it's on this orange box. It should be 0. We use this line, and under 5 it should be 0. But so the first feature is the better feature to divide these classes, to classify these classes. So that that helps us to find the interpretation of the model. Eventually, you want to explain how we best group these people. Okay. Our last question I want to mention is, say, do we have to do feature scaling for clustering? I didn't do that in this case, but do we need to do feature scaling for this algorithm? Feature scaling is changing all into 0 to 1, the same scale, same range.
No.
You don't think so?
Make
I
it all
was,
0, 1.
Uh,
What's the change? You make it all 0, 1, wouldn't it mess with your data when it comes to clustering?
it would change the data, but it would not mess up the data. I think. So, for example, if we have so if they are now, this is another group of data. If they are not, scaled, it could probably appear like this. because this y value, it goes from 0 to 1, but this x value x1, okay, this x1 goes from 0 to 1, and then this x2 goes from maybe like 0 to 250. So this one will be the dominating feature here. So anyway, this algorithm is also based on Euclidean distance. So you should scale them. So after scaling them, this maybe the distance between these dots will be far away. Then it will be easier for you to cluster them. So it used to be all like squeezed together, and after you scale them, then it will be more clear. Okay, so you should use scaling because it's based on Euclidean distance. And another one is so feature scaling. We did a lot of feature scaling for like classification and the linear regression. However, here now we don't have the target variable. Can we do features? Can we use we cannot use the previous method we use, right? The previous method we use is to get a correlation and to find which one is highly correlated with the target variable y. Or we use this group bar plot to find which one is a good, which feature is a good feature to distinguish the other one, to distinguish the target variable. Or we use the box plots to see whether this x2 is a good feature to distinguish this target variable. However, in this method, we don't have a target variable. In clustering, we don't have the target variable, so these methods will not help anymore. And how can we reduce the dimension? How can we reduce the dimension? So there are some new methods. It's called principal component analysis. That's one method often used for dimensionality reduction also. And also you can make decisions with your own domain knowledge. Like of giving an example. Give an example of this clustering. So how do we use our domain knowledge to reduce? To reduce the dimensionality. For example, maybe we have a group of cars and we want to make them into clusters. Then you could probably you would choose those features like a brand, or you would choose all the cars, the age of the cars, those dimensions, right? Those features, but some of the features like color, or some of the features you may clearly know, those are not important features, so you can discard those. Okay. But yeah, you could like skip the step of feature reduction. But if there are a lot of features, you should still do that. Okay, let's conclude our lesson today. Everybody submitted your project? Oh, okay.
just a screen recording, right? We didn't have to record our face or anything.
Oh, you don't have to. You have to explain your report very well, like explain all the steps very well.
Yeah.
So,
Wasn't that scribble?
take the report.
Yeah, just.
Not the one I saw. Not the one I saw.
Yesterday, I submitted the new one. Yeah.
Oh, okay.
And I re-recorded the video as well.
Oh.
I'm just trying to figure out